Okay, we're going to deal with our first classification method, and that is the equal interval classification. Oftentimes we use this as a naive approach, and what I mean by naive is not that you're naive in doing it, but that it's an approach that people can understand without having much understanding of mathematics or of the data itself. So again, in this case, each classification interval encloses an equal amount of the range of the data. Okay, so again, if we have 1591 as our maximum value, and again, we're going to be looking at total population within our block groups, and the minimum range is 0, well then, if we want 5 classes, we're simply going to divide 1591 by 5, and we end up with 318 as the class interval. So 0 to 318, 319 to 636, etc. And in this case, what we can see is that each interval is equal. Now, this has a certain advantage to it in that, again, as I said, the easiest thing is that people see it and they understand. Equal number, equal number, equal number. It's very good when the data that we're looking at is continuous. So, for example, precipitation data or temperature data, depth data, elevation data, all of these things lend themselves to an equal interval form of classification because we want to step through the data incrementally. Unfortunately, for many human phenomena, it's not very good. If the data is clustered rather than evenly or normally distributed, and especially in a normal distribution, it's a very, very tight cluster, it may be very difficult to see variation. And in fact, especially with outliers, we may have almost all of the data pushed into a single class and then the high or low value sitting in its own unique class. So let's take a look at this. In the first case, what I have here is, again, an equal interval. You'll notice this is total individual population in each block group. And you can see that our class is here. And we're getting kind of the distribution that I talked about in those disadvantages. In other words, we have one area right here that's in our highest value. And then we have almost everything else in our low values. We have a few in the intervening values. In fact, so we have 1 here, a few in this, 2 in our second to highest value. And so that represents a real problem in losing a lot of data at the low end. And in this case, if we were to look at the histogram of this data set, what we would see again is it's very much not normally distributed. And you'll notice a whole bunch of values over here in the low class, and then we have one way out here. And so that presents our problem. Okay, now, what we can also see, though, is that if our data is natural or is normally distributed, and what I've done here is I've normalized the population of each block group by the number of houses. And if we look at its distribution, we'll look at its histogram again, what we can now see, again, still equal interval, but in this case, you'll notice that our data is much more normally distributed. We still have an outlier out here, but these outliers have much, much less effect on this. In other words, really in our core of our data, we have 1, 2, 3 classes that really cover the majority of our data. And so if we look at this one now, what we will see is that in fact we see most of the data is broken into unique classes here. So we have our low class, and we can see where the lowest values are throughout here. And we see our mid values throughout kind of the northern 2/3 of it. And in fact, we see our high value up here. So we can actually interpret the data a little bit better in this case. Now, if this data was evenly distributed, then we'd have a very easy time evaluating it. Okay, in the next one, we will be looking at a natural break as opposed to an equal interval break.